Thank you very much for the introduction. I'm Arvid. I do basically internet-connected microelectronics, like before the IoT existed, or before it was a hype, basically. It existed before that. I'm an expert in connecting stuff to the internet in massive scale. I'm going to talk a little bit about what massive scale actually means and why this is so different than from what you heard about IoT in the sense of hacking some Raspberry Pis. And I currently work for Superscale Wireless. And let me fly over here. And for High Five. High Five is an agency in Berlin for hardware startups. As I said, we're going to talk about massive scale embedded devices. So first of all, I'm going to introduce you to what massive scale actually means. The second thing I want to talk about is something that we discovered during specifically continuous deployment that could be really interesting for people doing continuous deployment in hardware. It's like how you actually face those challenges that you have during hardware testing and try to migrate the old world of we're doing hardware in the basement to a more like, I don't know, modern approach that you know from software development where people actually can do stuff like continuous delivery and work a little bit more flexible, a little bit more agile. Next thing I want to do is introduce you to over-the-air upgrades over specifically how it fits into the continuous delivery pipeline. And if we have the time, just so you know, if you have any questions, please just interrupt me. I'm perfectly fine with taking this whole different direction, with going somewhere else. As I said, I do massive scale hardware. If you have any questions, just drop them in. If you find any point that's appropriate for everyone, just drop your question in, and we can go there. And if you have some time, I'm going to talk a bit about how the embedded built environments, how the existing ones, how they scale in terms of massiveness. Like if you build like millions of devices, what is the kind of challenges that you have? And we're going to talk a little bit, if we have the time, hopefully not, about vendors, because vendors are really, the guys who actually build hardware, they don't really know software, so it's kind of like, it's a challenging field that can be really interesting to explore. So when you think of Internet of Things, like in terms of the word that just is everywhere these days, what people mostly think about is stuff like Nest. If you don't know what Nest is, it's basically a thermostat, like a controller for your AZ that you put in your home, and it's like smart and everything. Maybe Raspberry Pis. You definitely know what a Raspberry Pi is. You might not have heard of Pratical I/O. It's basically like a GSM device that you connect to the internet, and you can download code from your browser onto the device, and all the internet connectivity is done for you. It's really cool for hacking stuff, like for creative people, but that's not what we're interested in. This is Internet of Things and all the hype and stuff around that. What I actually build are things like this. When I talk massive scale, I'm going to talk about millions of devices. Specifically, we have, for example, residential internet gateways. These are IoT devices. They're internet-connected hardware. There's embedded software running on them. With 3.37 billion devices in the world, for example, connected to the internet. Or we've got 6.8 billion smartphones, stuff like that. And then there's the 500K Teslas. So that's not a large number, but it's definitely a large economical impact in terms of these are the first cars that have a constant internet connection and actually use it for software updates while driving. So those guys actually did the right thing in terms of we're always connected. I'm also going to get to that. I think I'm going to not talk a lot about that. If you have a hardware startup, actually, let me just do a quick poll. How many people of you have actually worked with hardware before? That's approximately a quarter. That's pretty good. Because hardware is coming, and everyone wants to do hardware because software gets kind of boring, and everyone wants to play around with stuff. But people forget, like, one thing that I want to give to you is hardware is done at massive scale. Like, if you're talking about building a startup around hardware, don't forget that you need to build millions of those things. Otherwise, you're not economically viable. Unless you have, like, a special product, and it's not a consumer product or something like that. But usually, people build consumer products, and you build millions of those. Because of that, it's a waterfall business. So you plan the thing, you design the thing, you go through all these different processes, and for each process step, you have like millions of tests that you need to run. There's also governmental thingies, like you need to pass a few tests before you can actually ship a device to consumers, like CE and stuff like that. And those are usually done in the classic process of how hardware is built. And then after that, there's the software people. And if they have like any modifications to the hardware, then you're basically screwed, because at that point you're already producing all of those. Because of that, we have these massive test suites, which are, I divide them in 3 categories. There's people who think different about them, but this is basically, here's a bunch of examples of how I divide them. I divide them in tests that you do when you get a device fresh from a vendor, which is stuff like bring up tests, basically means does the device boot without going into flames. Then there's acceptance tests, which is like, does it meet our requirements? Does it actually, I don't know, have the CPU power that we wanted? Does the accelerometer go the way we wanted? And stuff like that. Then there's compliance, which is regulation stuff like EMIs, electromagnetic interference, stuff that you actually need to do in order to use the device safely. And then after that, it comes software development. And you all know the software development testing environment, like functional integration, regression, all that stuff. You know how that works. But that's a whole different world from like what hardware testing really is. It's like totally different. Not in the sense of that they're testing different stuff. More like the way that people think of them is totally different. And then when you go into production and build millions of those and got to do stuff like aging tests, for example, which basically means like how does my device behave over time? Like does it get, I don't know, does it break over time, stuff like that? Does it maybe heat up because our batteries management is bad or something? And after a year, your battery explodes. This is stuff that you do. Also Verdon tests, like how many times can I flash a device before it breaks? These are interesting things. So these are the 3 categories I use. And really what the challenge is when you're a software developer and hardware startup is how do I integrate these tests that I have, like these software tests. I just want to have, I'm writing my app for this phone, for example. I mean, my low-level app, right? I'm not talking about apps on top of it. Like, I don't know, my boot manager or something like that. And I want to run my functional and regression tests and all that stuff on these hardware test infrastructures that are usually absolutely abysmally terrible. Like, when you get a new device, you usually get very few of them because they're really expensive to produce, and you got to make batches of them because you might change things, etc. And then you have like this one hardware guy who, I don't know, builds a jig for you. A jig is basically something like that you see on the cable thing, usually with a physical attachment on top, where it can actually test the thing for real, rather than just going in there by SSH or something like that. These things allow you to do more specialized testing. But these are really made by hardware people. And also, although the tests are made by hardware people, everything is made by hardware people because software people don't understand that stuff. It's just too hard. Then you run into issues that these things look like that. I mean, this is just a kind of like overdone example of what people do in test script. This is literally something I remember from working at Nokia, where I did the Nokia N9 testing infrastructure. People do, like in the factory, they give you tests like this. They basically have a shell script where everything's prefixed by sudo. And then they install some stuff that never existed, break some stuff in your proc file system or def or whatever, and sometimes it's even written in a way that never worked before. Things like you have some, for example, flashing on the device, flashing new software is usually done by either automatically detecting the one device that is attached to your PC, or it's hard-coded where it is. Same for like anything that's with USB. They usually just explore the USB bus and check which device is attached and then use that one. It's not like you could, those tools have like a suite or something where you could tell which device to use. Maybe if you have multiple attached, you're basically screwed already because those scripts don't work. Also, you can already see that I'm not going to execute a script that comes from, I don't know, China, where everything's prefixed with sudo. It's not going to happen, right? But sometimes you got to have to because you have, I don't know, 600, 700 tests, and you got to run all of them. You're not going to go through that and fix all of that stuff. So the solution people, I worked in an office in Nokia where people actually had solutions like this. They would have like this one dedicated Windows PC where you would, that was basically sacrificial because they would reinstall it every week because it was broken after running all of these tests with all these pseudo scripts and stuff like that. You also had to run Windows and Linux in parallel because the scripts are in Linux and some of the tools are Windows and stuff like that. It's really bad. But anyway, so the solution for that would be that they had something like that, which exposes the TTY, so you know what the TTY is, basically the serial terminal of your device to your local area network. So you could access it from across the room, And instead of using your own PC, you would use that one sacrificial Windows PC in the middle of the room. And everyone will just scream, I need to use the test device now. Please, can everyone get off the TTY? People still work like this. I've seen still people work in 2016 like that. Please don't do that. It's really bad. You're just wasting your time. And sometimes you need to reset hardware because hardware is, there's nothing underneath. There's no controllers. So if it gets stuck, it's just stuck. The only thing you can do is pull power. You sometimes have USB controllable PSUs that you attach. When I came to Nokia, I was like very young and I was ambitious and try to fix things. And I said, guys, we really need to have continuous integration because what you have is just bad. The only solution I did see back then, even back then, it was like 5 years ago, something like 5, 6, 7 years ago, something like that. The only solution I really see to any no, that's bullshit. To any bad software is Dockerize it. Right, if you have something that's really shit and you want to isolate it and damage control it, the only thing you can do is like put it in a Docker container and just leave it there and hope it doesn't escape. And that's something that interestingly became a concept after that. Of course, what you cannot do, you can't, the slides are in the wrong order. What you can't do is you can't Dockerize hardware, or you can't like emulate your hardware inside the Docker container and then run all of those test scripts, because the testing infrastructure of hardware is based on hardware, and trying to emulate that is just, nah, just don't do that, right? Just buy more hardware, or I don't know, just try to get your hardware working rather than trying to emulate it, because you would basically rebuild your hardware and software. It's just useless. Instead of Docker, back then Docker wasn't that popular. So also, it's going to tell you why Docker still doesn't work, actually. You can use pretty much anything that uses kernel namespaces. I mean, Docker is built around kernel namespaces. LXC is built around it. What else? Pretty much, like we heard before in the talk from Leonard, for example, that systemd nspawn is based around the same infrastructure. It's all the same. Really, you can use anything there. And back then, we decided to use libvirt. And the way we fixed our testing infrastructure was, it's called Hub Agent. It's an open source project you can download in GitHub. Basically, the idea is that you have all these things that you need for a test that used to be on the sacrificial PC in the middle of a room, are now inside a virtual machine and isolated completely, but you can have multiple machines on one host because you can isolate them through USB, because everything's pretty much USB. Even like back then, everything was USB, or you can emulate it over USB or something like that. So the idea that Hub Agent is that you have, for one test setup, which consists of a target device, like anything you have, in this case it's phones, but it could be any target device, could be a Raspberry Pi or something like that, right? You also have some peripherals that you need, like a controllable PSU, for example, or a flasher device that's also a USB. You attach all of that to one USB hub, and then you tell a Hub Agent that this USB hub is attached to one libvirt instance, to one virtual machine, which again hooks into Jenkins. And you can have multiple of those. You can have just infinite of those, pretty much. The way it works in Jenkins then is basically the whole thing works like that. It's pretty easy. It's pretty simple. When you attach a new device to, let's say you attach a new USB hub. You attach a new USB hub, and UDEV will tell Hub Agent that there's a USB hub attached. And then Hub Agent will spawn a new agent for that. New VM, new virtual machine with all the stuff pre-installed that you defined previously, what you want to have in your test environment, including the Jenkins agent, for example. If you're using Jenkins, if you're using anything else, would pretty much work a different way, of course. But in our case, we use Jenkins. And it would register that with Jenkins and say, hey, I have a new virtual machine here. Jenkins has this thing, this plugin. It's called, sorry, I forgot. It's libvirt something. It's a Jenkins plugin. But you can also tell it to not spawn the virtual machines itself, but wait for the virtual machines to be spawned by something else and then be registered into Jenkins after that. And that's what we do here. Like every time you attach a new USB hub to the test rack, it will spawn a new virtual machine for that. And then when you attach physical devices to that USB hub, the Hub Agent will set the proper label for that USB device in the Jenkins client or Jenkins builder. so that you can run jobs like, I want to run this test job on, let's say, on the hardware version 4. Jenkins will automatically use those label version 4 thingies, where actually we do it by USB IDs, because it's easier, because it's less configuration issues. So if you find those USB IDs, then run the job on those agents that have this USB ID. That's really useful for if you have multiple revisions, as I said, or if you have multiple peripherals. Like sometimes you want to do stuff like physical testing, environmental testing, and you might have a USB controller on your rack that does freezing of the device or something like that. And you don't have to configure where that virtual machine is actually spawning when you use Jenkins labels with the USB IDs of the controller that you want to run on. Nowadays I work for a different company and we use the same thing, except we now use Docker, because Docker is the hype and actually the word is kind of crap. Sorry. We do a little different setup, because in Superscale we do Wi-Fi access points, or like Wi-Fi infrastructure. What we do there is we have, like, again, a USB hub and a switchable power supply and then a network controller, because isolating network is just, way too boring. Why would you do that when you can just do USB network thingy, right? And just attach that into the same infrastructure, and then you can configure that with stuff like some tests on these wireless access points that we need to test. They have fixed IP addresses inside their test scripts. And you couldn't run that within a rack of like 20, 30 of those if they weren't isolated. Sure, you could isolate it on VLANs or stuff like that, but it's all really boring. If you can just do USB, it's great. USB works generally great for isolation. That's really the message I want to give you. If you want to virtualize hardware in the way that you need to virtualize it in a test rack, do it over USB, everything, because USB is really good for that. Also, Linux just supports that really well. The isolation support on libvirt is great. It actually really isolates it. It's not like that it can cross boundaries or stuff like that. Not like Docker used to. The way USB inside a Docker container worked is that you bind mount the USB tree inside the def USB tree. That's no longer the case. You can actually literally transport the device mounts. All right. That was rather quick. If you have, because that's pretty much all I have to say on libvirt hub agent. So if you have like any input or something like that, now would be a good time if you actually thought of something. Because the next topic's not going to be about, it's going to be about over-the-air updates.
Anyone?
All bored, fall asleep. Okay, it's fine. I'm just going to continue then. All right. Another thing I want to tell you is how over-the-air updates fit into your continuous delivery pipeline. It's, in my opinion, when you do massive scale hardware, over-the-air updates is something that a lot of people forget when they start their hardware startups with stuff like, I don't know, I have this cool idea, I want to do it in hardware, and then people forget that in the continuous delivery pipeline, you actually need ODAs, because you actually need to deliver your delivery to your customer. Sometimes people tell me, oh, we don't have internet in our device, so we don't do updates. We do offline updates. I really advertise that you do not have physical devices without internet being built in 2016. I'm going to tell you why. This is an example of some people who thought the same way. We have approximately 1 million SCADA systems exposed to the internet. SCADAs are like machine controllers. They're like embedded. There's an embedded software in it. They're like kind of like the stuff people build in hardware startups, controllers, basically. And people didn't think that they would ever be exposed to the internet, so they didn't build an OTA. Nowadays, they're used in pretty much everything. Factories, nuclear plants, hospitals, clearing stuff like for public transport, and all sorts of things they're used in. And they're all connected to the internet because, it's the internet is there now and everything's connected to the internet. So they connected those things to the internet. And what happened was that they're really vulnerable to a lot of stuff. And they don't have any OTAs, and it's kind of like a security issue for all of us. They're critical infrastructure. There's a whole security talk about that from the SecCon and stuff like that. Black Hat conference, they talk all about this stuff nowadays because it's really bad. It's like in critical infrastructure. So these guys didn't, I hope they learned from it, and they know now that even if you think your device is never going to be connected to the internet, eventually it's going to be connected to the internet. So you should really prepared to be prepared for over-the-air updates. Some technical stuff, how over-the-air updates actually work, is like this is basically how any embedded device looks like. It might be named differently or it's differently implemented, but really it works all the same way. You always have some sort of bootloader that comes from your vendor, like the guys who actually built the physical thing, and only those guys know the thing because they get the documentation from the CPU vendor and they can actually boot the thing. In x86 in your laptop is called BIOS. It's pretty much the same thing. And after that, you have some factory calibration code that also happens in the factory. Stuff like when you have an accelerometer, for example, there's calibration code in there that it will actually calibrate for the errors in the factory. Or stuff like wireless calibration is done for the antenna on there, for example. And that's also stuff you just don't touch. And after that, you have usually two partitions. One is the system, where it's basically usually read-only, except if people do weird stuff. Sometimes they do it read-write. I really don't like that. Which is where your system comes up, and then you have a config state, like this is the read-write partition where all the user data is. This is basically also how Android works. Like if you ever wondered how Android system reset works, like when you press factory reset on Android, it actually just deletes the user data partition. It doesn't delete system. And it just gets to a blank state basically that way because system is never written to, usually, unless you break it or root it and do weird stuff to it. Right. Quick word on how the build environment fits into the delivery pipeline. Or basically how they fit into the delivery pipeline at scale, which is really important if you think in scale, which you should if you do a hardware startup. I think there's 3 different categories of build systems for embedded system. One is the package-based ones. These are pretty much what you're used to from your standard Linux distribution. They work the same way, and I'd say their whole USP is based on them working the same way as your Linux distribution. Kind of like the tools you're used to, like Yum or this was a thing called, I forgot, Zipper? Yeah, that thing. They pretty much work the same way, and that's the advantage of them. And then there's the system-based ones, which basically build the whole system in one go. And then there's a bunch of really terrible hacks that I don't recommend because I know them from Nokia, like Scratchbox do. Don't do that. Pick one of those two. Either you want to go package-based or system-based. Just something that immediately sticks out when you look at those two things and look at who's actually using them. Package-based systems are usually used by, let's say, the IoT economy, and system-based stuff is usually used by companies who actually build devices in the millions. And there's a good reason for that. There's actually 2 reasons for that. One of the reasons is that package-based distributions are really terrible to test. Like testing the whole image and passing certifications and all of that is really difficult because you actually don't know what comes in there. And the other thing is really that working with package-based distributions in continuous delivery is really hard because you can only test code after it was built into a package and built into a distribution. And that distribution you can test, and then you have an error in there. You know that if you build Linux distributions. In system-based, it's a bit different because you built the whole thing in one go, and that's pretty much the requirement for continuous delivery, in my opinion, is that you can build your entire system just in one go on your developer machine or on a build server, it doesn't matter. As soon as you change one line of code, you just built the whole thing, flash it, you can test it, and you're happy with that. Yeah, you can see why those things are used. For example, why Android is a system-based build environment. It's just because people really need to be able to change this little thing for this little hardware, build the whole thing, put it in their CI system, and get a result, like a constant feed of results from their things. Android really has an extensive CI build system, actually. Same arguments. There's always like this short discussion of, hey, we really want to do package-based updates, and you know that's why we use, like, let's say Yocto or something like that, because we think that we want to go in the field and maybe update, I don't know, libz on this specific hardware and not on the other ones. That's all fancy. That's probably really cool during development. But the thing is, if you have 1 million devices out there. Let's just imagine your startup has 1 million devices out there. You're not going to SSH into 1 million devices in update packages. Just, you know, it just doesn't happen. I mean, just think of that. It's just crazy. And also, the risk of doing that is not just the time it takes. You could automate that. The risk of that is massive because you have to guarantee, like by your contract that you have for you, the consumer, you have to guarantee that you're not breaking it. And you don't know if you're not breaking it because you're just updating a tiny part of the system. And you would have to integration test that basically after you put it on the customer's device. That's not really what we do in embedded. Embedded, we do full image updates because we can put the full image on our test rack in a continuous delivery pipeline and then be absolutely sure that this thing is going to work on like all of these devices that we tested. Like we test like 200, 300 device categories with, I don't know, 700 user configurations maybe. And then you have a couple of thousand tests and you're absolutely sure that everything that's out in the field will actually work with a new system or device. You cannot do that if you just have, just think of the complexity of trying to test that with package-based systems. And that's also what it means in terms of scale. What people forget in scale is also the amount of support that you're generating by doing that, right? If people call you and they're like, I don't know, my HDMI output is broken since the last update of, I don't know, they're probably not going to know that there's like a component of the system being updated. And the reason that, for example, Android has versioning that's fixed, like everyone with the Android version 5.1 has exactly the same HDMI output driver, for example, and that's also something that your whole support pipeline knows. So like, you know, one of those critical arguments that you have in scalable hardware. Oh yeah, I have the slides in wrong order. Amazing. So we're going back to continuous delivery pipelines in building stuff. Back before the hub agent, back before we could do automated testing in massive scale, really, or before we could run these 700 tests, suits, thingies, automated. What we did, for example, in classic phones. I mean, the reason there's a 3310 Nokia on there is because I'm not allowed to show you the actual Nokia phone that we worked on after the N9 because they're all killed. Microsoft didn't like them, so sorry. They were really good. So before we had all this automation, you had that problem that one guy would git push something to the giant repository, and another guy who was responsible for building stuff, literally responsible for building and integrating stuff, like a person, just responsible for integrating and building. The reason for that being the shitty setup that I showed you before, which is that the hardware requires specialized setup. And they would pull it, they would build and test it, and then when the tests were successful, whatever they were doing, they would roll it to 1,000 customers. You wouldn't notice any of that, usually, unless you're one of those unlucky 1,000 customers and you got a broken update. But then, you know, calling back 1,000 phones is a lot cheaper than calling back 1 million. When none of those 1,000 customers called you, then you roll it to everyone, or roll it in stages. Like sometimes you do country-based stage rolling. The reason for that, behind that, is that you already prepared the legal work for calling back all of those devices in case you break them, for every update, basically. And that's why they do country-based rollouts. Now that we have continuous hardware, it's a lot cooler because now you can actually do git push, and you have this Jenkins stuff, and you build this OTA package automatically. You can test it on a rack on all those various variations that you need to test on, and you get direct feedback. Really, this only works if you have a system that builds in one go. And then you're actually a lot happier because you have a continuous delivery pipeline. Because then you can put that OTA image that came out of that. In theory, you could also roll it out to customers. Of course, there's a whole lot that has to go after that, like organization-wise and stuff like that I'm not going to talk about today. But in theory, you could directly, in technical terms, this is continuous delivery because you can directly roll it out. OTA, really good stuff. Okay, we're done with OTA. So still no one woke up to have any input.
How you design them and manage them
Right, that's actually on this slide. The answer to that is on this slide. So your question was, just to repeat it for everyone, if you have different hardware variants out in the field, like actually sold devices out there in customers' hands, how you manage those large scale of test cases that you have to have. Well, the trick really is here that there's 2 points to it. One of the points is if you have a virtualized setup like I've shown you with that one, you can have an infinite number of test setups. Like you can have different hardware variations and they all work the same. And you put them in one rack and you have basically you can run them in parallel, right? Unfortunately, the full test suite for everything, usually at least on phones, takes like still 6-7 hours. So really what you can do, at least what I usually do, is have different stages of testing. One of them is that you get direct feedback. Usually that only happens, you switch off all the hardware tests basically, because you can kind of, especially all the governance stuff, like the stuff you need to test in order to comply to certification and stuff like that, it's really boring and no one ever breaks it. So you can just test it, you know, in a second stage after that, like let's say on a new Git tag or something like that, right? But what you do continuously during your day-to-day work is just you test like a small portion of it, preferably just the software part. And that takes a lot less time, and you can still do it in parallel in all of these variations.
So mostly you use like 3 different suites which when you run depends on what have been changed, right?
Absolutely, that is correct. You also can, if you have a larger software stack, you can separate that into different stages. Like you can say, okay, something in middleware was touched, so I'm only going to run the middleware suite. Or something in like the driver part was touched, so I'm going to run the full hardware suite or something like that. But still, at the end of the day, for every Git tag, you need to run the whole thing, just because that's just continuous delivery. Because you need to know if you can actually roll it out to customers. It's also an organizational problem, right? You need to know in management at any point in time, you need to know if you have a build that actually works, right? If you're in time. You mean in OTA? Yes. OTA, well, it depends. There's different strategies. Depends on like your decision making. For example, in Android, we don't have rollback. We just never make mistakes. No, I'm just kidding. It's always forward. So if you have a bug, you just go to the next word and be after that. Then there's different strategies. Other people think different. They have rollbacks, but that's really like a system-dependent implementation of how you implement OTA. You can always, if you look at their stuff, there's another rollback strategy that's called double buffering. A lot of people use that. I didn't show that here. When you have smaller devices, like things that don't have a touchscreen, that don't have user interaction at all, you usually do double buffering, which means that you put another system there, like another partition with another system. And the new system will go to one of those. It will boot up, and it has to, within a certain period of time, it has to make a self-check. And if that self-check fails or timeouts, it will go back to the bootloader, and the bootloader will know, oh, I just booted that system, and that system never passed the health check, so I'm just going to boot the other one. Right? That's also something we do in very small devices, like in IoT devices, basically, because you don't have a way to recover them as a user. All right. There's supposed to be a timer here. How much time do I have? Oh, thank you. Yeah, it's not helping if the timer's pointing towards you. Okay, thank you very much. It's not ticking? Anyway, whatever. Just interrupt me. So a few words that I want to lose on vendors. When you work with vendors, specifically get hardware for them, and you also have to run their test suites, simply because of governmental issues. There's one thing that I learned when doing hardware is that the people doing the actual factory tests, they're not going to listen to you. Ever. Like, you can basically tell them, please test the display to be working during, I don't know, when I pull the battery or stuff like that. They're just not going to do it. They're going to say, yeah, we tested that. There's some manager who tells you, yeah, they tested that. The manager probably sits somewhere in the US and never actually has spoken to anyone in the factory. So you need to do that stuff yourself. Also, a bit of funny story that I learned, for example, during my work in Superscale. The hardware vendors have the tendency to be agile. You could call it agile. Actually, it's opportunistic. Sometimes you rely on them giving you something that works according to specifications. You test the specifications on one device out of a whole container of devices, and it works. It works just fine. And they give you a paper where it says, we literally tested all of those 1,000 devices in our yield testing. Yield testing is when they literally put the board from the soldering placement machine, they test if it works. That means nothing, right? That just means it kind of turns on. Really, it doesn't mean that it will actually be a device that's functional. Sometimes, and the reason for that is sometimes they change chips during a placement. Like you order a container and you hope that you only need to test one out of those containers, but actually in those containers are 3 different variants because sometimes they feel like, well, I found a box of this stuff. It's kind of compatible in terms of hardware, right? So we're just going to put that on. And the yield testing says it's positive because the electrical lines work just fine. But maybe they were really funny and sold a completely different chip on it that has nothing to do with the software you're running, right? And they don't care. They're like, well, yield testing works. And the specifications you gave us were just, put a CPU in there. And I'm like, no, that's not what we said, but thanks. What I used to do is, what I now do is I actually have people go through every single box in a container and check every single label if there's a variation change. Like when it goes through the whole shipping pipeline where I, as an engineer, am usually not involved, I still have someone look inside the box, look at the label, and check if there's a variant. And sometimes you even need to go down and look at the actual chips that's on there and look at the labels and see if there's a chip variation change, because that can really have a large impact on your software, just because it could even be, stuff that happens like there's a CPU vendor who just puts a version 2 on something, but in reality, it's not actually their own CPU, it's just someone else's relabeled, and it's compatible, and then they called it version 2, and then you're screwed because your software is not compatible with that. Stuff like that happens, so beware of that when you do massive scale hardware. Fortunately, continuous integration, it's like when you do parallel testing with all the hardware rack, you just need to detect it, and then you can put it in your test rack, and then you're fine, right? So we're not going to die from that anymore. Yeah, people used to screw up things like that. For example, in Nokia, we had like this really funny issue when, like I think it was a Symbian phone or something like that, where they were in the test rack, where we're seeing that the device, like all of the tests were failing all of a sudden with a specific variant. And like people were like, oh, did we break it or something? Did we break the test? And it turned out that the CPU desoldered. That stuff happens. And when you have all the variants in your rack, you can see that stuff also. That's really boring. I'm actually going to tell you about that. So I think, how much time do we have left? I really don't understand the clock. 10 minutes, perfect. So usually that's the time I take to answer questions. If I want to give you any advice, if you're building a hardware startup, please implement continuous delivery early, because otherwise you're going to bite yourself in the foot if you do it later. Simply because some of the software decisions made in embedded software are just incompatible with continuous delivery. Stuff like we want to run Linux on it, full desktop OS. Don't do that. It's not going to work in your continuous delivery pipeline. Also think of massive scale, because eventually you're going massive scale. And that's pretty much all I'm going to have to tell you. Thank you very much.
Thank you so much. Do you have any other questions?
Can also tell you Nokia war stories if you want, like how we failed or something like that. But I don't think it's interesting for the audience.
You can tell what's that on the photo.
Sorry, what?
You can see what's in the photo as well.
Oh, this one is super scale, right? That's a whole different project. This actually, this is a shipment that failed. Like we actually picked that out of a container because it was a variation from a hardware vendor where they changed something, and all of these devices are failures. But they passed certification test. They just didn't boot.
Still good, at least a bit.